This is Radio Ecoshock with Alex Smith.
New climate models suggest Earth could surpass 5 degrees C of global warming, and that would be a disaster for all living things, including humans. But is there a flaw in the latest computer simulations? Our guest, Dr. Jessica Tierney, finds records of past climates suggest we may overestimate possible warming. With her specialty in paleoclimatology and organic geochemistry, Tierney has led or co-authored dozens of peer-reviewed papers explaining how the deep past can help us project the future. From the University of Arizona, Jessica Tierney, welcome to Radio Ecoshock.
Thanks for having me.
Well, as citizens on this planet, we need to understand what top climate negotiators like John Kerry for the United States will be told by scientists. Where do those climate projections come from?
Well, our projections for future climate all come from state-of-the-art climate models. Climate models are basically giant computer programs that are run on supercomputers. They're computationally very expensive, so it takes a long time to run these projections. So they're run over a series of years in advance of mostly the next IPCC reports, which happen, every 7 years or so, 6 or 7 years. So right now we're about to see the release of the sixth assessment report from the Intergovernmental Panel on Climate Change. That's going to be coming out later in 2021. In advance of that, all the modeling groups around the world have been running their latest and greatest climate models to predict how climate will change by the end of the century and beyond.
So these are called the coupled model intercomparison projects because they run in at least 40 different centers. And we're now on the latest version, which is CMIP 6. And before we get to your objections to the worst case 5.7 degrees C warming in those new models, I have to advise listeners that the old RCP system, the representative concentration pathways, appears to have been dumped. And that bothers me because the public was barely learning about RCP 8.5, and now that's out. Jessica, what is the new naming system for possible climate outcomes?
So the new outcomes are called the shared socioeconomic pathways, and really they're very much like the RCPs, but there's a lot more scenarios in them. And so one thing to keep in mind about the scenarios is that in addition to a different amount of CO2 emissions or other greenhouse gases, they also make assumptions about how countries interact with each other. For example, if there's international agreement to curtail carbon emissions, or whether some countries decide to burn a lot of fossil fuels while others actually ratchet back. And so there's this huge variety of scenarios, a big menu, but in reality, many of them have a lot of similarities with the RCPs. So in the last round with the RCPs, we had a relatively low emissions scenario, which was called RCP 2.6. The numbers on these correspond to the amount of forcing in units of watts per meter squared. So that's like a climate unit of forcing. So how much energy is getting put into the system by, mostly elevated greenhouse gases. So in the last AR cycle, we had these RCPs. 2.6 is the low one. RCP 4.5 is the middle one. And then an RCP 8.5, which was a high emission scenario. And similarly, there are SSP 2.6, SSP 4.5, and SSP 8.5, and for all intents and purposes, they're very similar. There's also some interim SSPs, though, like 7, SSP 7, so in between the 4 and the 8 extremes. And there's also a very low emission scenario, the SSP 1.9, which was designed to assess what would be needed to keep global warming to under 2 degrees Celsius.
Well, I gather the next synthesis report from the Intergovernmental Panel on Climate Change, as you say, it's not due out till January 2022, but parts of it will be available to governments at the Glasgow COP coming up this December. Will the data given to climate negotiators be too alarming, though, due to possible model errors?
Well, there's nothing inherently, right or wrong with climate models. I think the big question on our mind right now is this issue of climate sensitivity. So just to back up and explain what that is. Climate sensitivity is how sensitive the Earth is to a forced change in climate. So in our case, we're most concerned with greenhouse gases, right? So the more sensitive the Earth is for a given amount of emissions, the bigger of a temperature change you will see. And the units of climate sensitivity are the expected temperature change from a doubling of CO2. So if you were to instantaneously double CO2, how much temperature change would you see on the global level? That's the metric of climate sensitivity. And it really matters because, of course, it determines how much temperature change we'll see by the end of the century, or even sooner than that. Climate models each have a different climate sensitivity that sort of emerges from the physics of the climate model. Some of them are not very sensitive, so maybe they have a sensitivity that's closer to 2 degrees per doubling of CO2, and some of them are very sensitive, up towards 5 degrees of doubling of CO2. That would be a high number. So one of the things that has come up with CMIP-6 is some of the latest generations of climate models have a very high sensitivity. That includes some of the major climate models in the United States, such as the National Center for Atmospheric Research, NCAR's TSM model, as well as the Geophysical Fluid Dynamics Laboratories model, GFDL NOAA model. Both of them have, their latest versions at least, have very high climate sensitivity, which is, of course, worrying because that means for the same amount of emissions, we see more temperature change. So the question that has been on everyone's mind is, do we trust these models that have really high climate sensitivity, or are they too sensitive? And if they're too sensitive, that means, of course, their predictions are going to be too much climate change, right? Not as much as we'll see. So the question has been, how do we kind of narrow that range of climate sensitivity? After all, what is Earth's climate sensitivity? And that's where my research comes in as a paleoclimatologist.
Well, what happens to the new CMIP-6 models when they try to reconstruct climate during the last glacial maximum just 22,000 years ago?
Right. So that's exactly, what we set out to do in our research was to test these new models against past climates to see if they could reproduce events in Earth's history that we have some constraints on. So we took the latest generation of the NCAR model and asked it to simulate the last glacial period, the last ice age in Earth history, which was 20,000 years ago. Sounds like a long time, but for geologists, that's pretty recent. And when we asked it to simulate this ice age, we have a lot of geological constraints on what happened during this cold ice age. The model got way too cold, way too cold, actually. So beyond what any of our geological indicators suggested. So together, our indicators for temperature change during the last ice age suggest that on a global level, it was 6 degrees Celsius colder than pre-industrial. And the model started to predict temperatures that were 11 degrees Celsius lower than pre-industrial. So way too cold. And so that, first order suggests, again, that the model might be too sensitive. In this case, we're going in the other direction. During the last ice age, CO2 was very low. So it was around 180 parts per million. And so we're lowering the CO2 in the model rather than raising it, but it overshot that particular time interval. And so we, published a paper about that just to express concern that, okay, if this model cannot simulate this past climate correctly, maybe it's too sensitive and its climate sensitivity is a little bit too high.
And a wide group of scientists, including Mark D. Zelinka and your whole team, say CMIP models get the glacial past wrong because of assumptions about clouds. Are there strong reasons to focus on the role of clouds?
Yeah, absolutely. So clouds are, a long-standing sort of source of uncertainty in simulating climate changes because clouds act as a feedback on the climate system. So in particular, we're interested in the low clouds. And so when we say low clouds, we mean like stratus clouds. So if you live on the west coast of the United States or Canada, you're used to seeing a lot of low clouds off over the ocean. Those kinds of clouds, these thick low clouds, they reflect sunlight. So the amount of low clouds on planet Earth is actually an important regulator of temperature change because they're reflecting sunlight, so therefore act as sort of, essentially regulating how much energy is reaching the Earth's surface. So what happens in these climate simulations of elevated CO2 is that when you increase CO2 in some of these newer models, the clouds, these low clouds, disintegrate quite fast. So you quickly remove these low clouds from the climate system, from the mid-latitudes, but also from the high latitudes, and that allows more sunlight in, and it actually acts as a positive feedback, which gives rise to higher climate sensitivity. So in the past, actually, some of the older versions of the models didn't have as strong of a cloud feedback, and it might have been a problem. They actually might have been not sensitive enough. And we know that because we've tested some of the older models against ancient warm climates and found that they struggled to simulate the magnitude of temperature change for some of these past or ancient greenhouse climates. But it seems like recently we've kind of gone on the other end of the spectrum now, where the cloud feedback is very strong, which gives rise to this high climate sensitivity. And it's so strong that, you know, you get too much warming, or conversely for the ice age, too much cooling. Now, so one thing to keep in mind is the climate models that we use for IPCC projections don't actually simulate clouds in of themselves, because they're smaller than the grid scale of the model. So the model is broken up into all these little, cubes, and all the physical equations are solved for that cube in the atmosphere or the ocean and so on. Anything that's smaller than that size of that cube needs to be what we call parameterized, which means that you write some physical equations to, essentially represent clouds, but there's no actual clouds in these climate models. So the tricky part is how you write those equations, and there's lots of different choices you can make. And they're all justified because, especially some of these changes in the cloud parameterizations have actually improved the match between the models and observations of clouds from the satellite era. But we're seeing some problems when we take those models and then extrapolate them, right, out to warmer or colder climates.
Yes, we interviewed Tapio Schneider from NASA about cloud formation and the carbon in the atmosphere, and I refer listeners to my Ecoshock blog to find a link to that program. And you and lead author Zhang Zhu, along with Bleisner and Paulson and others, have been raising this objection about global cooling failure in the latest climate models for at least 3 years. What responses are you getting from the climate modelers about this problem?
Yeah, well, I think there's sort of a little bit of a historical reluctance to trust the paleoclimate record or the past climate records. So, folks who are developing climate models, they really seek to make sure that the model can reproduce observed climate, and especially satellite era observations, because this is our most complete picture of how the climate system works, right, with clouds and troposphere and stratospheric and everything. And obviously, when we go back into geological time, we don't have that kind of resolution or specificity. However, on the flip side, the changes in climate in the past are huge, right? So 6 degrees Celsius global cooling, that's a huge climate change. And so the signal is large, even though we don't have all the details that you have from the satellite observations. So one of the things that we've been trying to kind of reach out to climate model developers about is that actually, yes, you can use these ancient climates as a way to benchmark your model simulation, because even though we don't have all the details of the climate system back in the past, we do have these massive signals. And when you think about it, what we're trying to do for the future is we're trying to predict climate change under a lot different CO2 than what we've observed over the 20th century, right? So we are going way outside of our historical observations. And so you could argue that in order to really understand what will happen, we need to study ancient climates where we do see these huge changes in CO2 and these huge changes in climate to essentially calibrate our climate models to that. So, what we've been doing is having these conversations with modeler developers and trying to encourage them in the next round of model development, which will be for the 7th cycle of the IPCC, or CMIP 7, maybe run some paleoclimate simulations out of the box and make sure that your model isn't too sensitive or not sensitive enough. We're at the point where we have enough constraints from the geological record that we can at least benchmark things like global temperature change and even in some cases the patterns of temperature change. So why not use those ancient climates to improve our ability to predict the future?
You are tuned to Radio Ecoshock. I'm Alex Smith. Our guest is scientist Jessica Tierney from the University of Arizona, and we're looking at ways climate models may influence next steps in the battle against climate change. Jessica, why do scientists assume the same mechanism or formula for global warming works for global cooling?
Well, they're not exactly the same. So when we go back to the last ice age, we have to contend with the fact that there is a giant ice sheet over North America, the Laurentide ice sheet. There's also a huge ice sheet over Eurasia. So some of the climate forcing for the cold climates is coming from the fact that we have these huge ice sheets. They're bright and white, and they reflect sunlight back to space. So that is an additional forcing on top of the changes in greenhouse gases. However, we're able to kind of pull apart the impact of the ice sheet forcing versus the greenhouse gases when we study the ice age. We can pull those things apart in part by conducting simulations where we only have an ice sheet or we only lower the greenhouse gases. And a lot of that, the impact of the ice sheet is sort of on the patterns of change. But ultimately, the response of the climate system to CO2 remains remarkably constant in the last ice age. So when we calculated climate sensitivity of the Earth system for the last ice age in a recent paper, we got a number, 3.5 degrees per doubling of CO2, that is right in the middle of the sort of expected range from the IPCC reports, from the expected range that goes all the way back to Jules Charney in the 70s, which is between 1.5 and 4.5 degrees C per doubling of CO2. So we find that the last ice age is right in the middle of that range. So that tells us that nothing super unusual is going on, and that in fact the Earth system is behaving more or less as expected.
I guess what I'm asking, if it takes energy to thaw polar ice, like the Greenland glacier, does that act like a brake on climate change? Does it slow down or almost hide the true energy imbalance we've created with greenhouse gases? And if so, when a lot of polar ice disappears, could Earth then jump up to the real heat we created?
Right. So, yes, the answer is there is this sort of positive feedback, and it goes in both directions. So, on the one hand, if you have a planet with a lot of ice, you reflect a lot of sunlight, a lot of energy coming in, and therefore you have a cooler climate. But once you start to melt the ice and expose darker land, then that darker land will absorb more and more heat, the temperature will increase even more, and you'll melt even more ice. So once you start the process of melting ice, then you have this positive feedback that accelerates the system. And that's why, for example, there's times in the transition from the last ice age into the Holocene, once the ice sheets are gone. Some of those, melting events of the ice sheet happen very quickly. So there are some fits and starts and times when the ice sheet really drew back, and we see, for example, a big change in sea level that's happening. It's not necessarily a smooth process because of this nonlinear interaction between the receding ice sheet and the amount of energy that the planet can absorb.
Jessica, could you please talk to us about, as you say, the language barrier between climate model and proxy data?
Sure. Yeah, so you think about, how do we know about these ancient climates? We don't have a thermometer, 50 million years ago when, in the Eocene when there's no polar ice and temperatures are so much warmer than today, right? We don't have a thermometer in the last ice age. So how do we figure this out? So we have to use what we call climate proxies, and these are stand-ins for things like thermometers, all the instruments that we use today to monitor the climate. We don't have them in the geological past, but we do have physical and chemical and biological things that are preserved in the sedimentary record that record climate changes. So there's a lot of different kinds of proxies out there that we can use to piece together the past. I'm sure that the listeners are familiar with, for example, tree rings, and that trees change the width of their ring depending on the climate. Sometimes they respond to temperature changes, so they'll grow a fatter ring when it's warmer. And sometimes, like here in the Southwest, they respond to water. And so when it's drier, they'll have a shorter ring. And so that's a simple proxy that we can relate to temperature or precipitation. Going back deeper into geologic time, like my work does, we have to rely on sediment cores that are collected from the ocean and sometimes from lakes on land. And so these are these tubes of mud. But in the mud, there's tons of stuff we can measure to learn about past climate. So an example would be in the ocean, we have these organisms called foraminifera, and they're little single-celled guys that make calcium carbonate shells, chalky shells. And actually, if we measure some of the chemical signatures in that shell, in particular isotopes of oxygen, it's an indicator for the temperature of the water. It can also tell us a little bit about how much ice is present on Earth's surface. And so that's just one example of a proxy. So in my lab, we actually work with molecular fossils. We work with molecules that are left behind and preserved in sediments that come from very specific organisms. For example, we work with one that is a certain kind of fat that's made by a coccolithophorid algae. And this fat is extremely distinctive, so we know exactly where it's coming from. And it turns out this algae changes the structure of the molecule in response to the temperature of the water. When it's colder, it produces fats with more unsaturations in it. And when it's warmer, it produces fats with less. We can calibrate this today by growing these guys in the lab, by also observing modern sediments. And now we have this powerful paleothermometer. So we have all these chemical tricks that we can do, also biological indicators like pollen, which tell us about changes in the landscape. So that's very important to see how the plants respond to climate change. But the question is, how do we relate that back to climate model simulations? Because a climate model will give you output in units of temperature, precipitation, and wind speed, and so on. And our geological information is in units of, isotopes, trace elements, these changes in these fats. So we have to bridge that gap. And that's done through statistical modeling on one hand, so developing models of how these different types of proxies work, what environmental variables they respond to, and we can test those models in the present day. We can also actually, using climate models, we can actually simulate a proxy, make a fake proxy or a pseudo proxy from the climate model output. So one example is you can actually put stable isotopes of water into a climate model, and that's very powerful because a lot of our proxies are based on oxygen isotopes, which I mentioned are sensitive to temperature. Also, on land can record changes in the water cycle. And we can actually now put those isotopes into the model, so they're already in there, and that really facilitates, comparing to proxies, because then basically you're speaking the same language, a chemical language.
Okay, so your team suggests that we should take past climates, including icehouse Earth, into account. Do you or does anyone know how to implement the model changes needed to do that?
Right, so we're coming back to this issue of clouds, and the question is, what we found is that a lot of the climate sensitivity in these models is related to the strength of the low cloud feedback. In fact, we were able to attribute pretty much all of the mismatch between the latest generation of the NCAR model and the LGM geological evidence to clouds. So that means that's the place to work. And the question is, how strong is the low cloud feedback? If it's not strong enough in your model, then you'll be under-predicting future climate change. Conversely, if it's too strong, you'll be over-predicting. So the challenge is, how do we constrain clouds in the climate model? Now, we don't have geological proxies for clouds. That's pretty tricky. But clouds are closely related to other things in the Earth system. One example would be sea surface temperatures. So as I mentioned, if you live on the California or Oregon coast, you're looking out over the sea and you see all these sort of low clouds, and it's there because the water is cold, right? Now, if that water was much warmer, there wouldn't be as extensive of a low cloud deck. And so it turns out that the surface temperature of the ocean and low cloud cover are very closely related because, of course, the low clouds are going to reinforce cold temperatures. And once they disintegrate, then the sea surface temperatures underneath them will warm up. And we do have geological indicators of sea surface temperatures. That's one of the things that we can do really, really well. It turns out the pattern of climate change is key here. So if you can reconstruct the pattern of past sea surface temperature change, you can link it to clouds. So we're actually, for future work, we're looking into ways that we can do things like, choose geological periods where we have a pretty good idea of the pattern of ocean temperature change. And then what we can do on the model side is we can, change those parameterizations of the clouds, tune them up, tune them down, and run a whole menu of different possibilities. And then we can kind of challenge that menu with the geological evidence of sea surface temperature. So what we think we can do is actually directly use the past climates to constrain cloud parameterizations. And there's a number of groups who are looking into that now. So I think that's pretty exciting work.
Well, despite your questions of CMEP6, you are a lead author on the upcoming Intergovernmental Panel on Climate Change, the IPCC, the Sixth Assessment Report. What is your subject area in that report?
So I'm a lead author on the chapter that focuses on the water cycle, precipitation, evaporation, flooding, and drought. And so we're tasked with assessing anything and everything associated with, rain and lack thereof. It's actually a new chapter for the Sixth Assessment Report. The fifth report didn't have a specific chapter focused on water. But it's a very important chapter because, so far we've been talking about temperature change here, but in fact, changes in rain, changes in drought are of big concern. And I certainly feel that living here in Arizona, where we're constantly worried about not having enough water and how that will change in the future. So it's been a really interesting experience to interrogate, the predictions for the coming century and try and zoom in on some regions and discover, what are the models saying about how the water cycle will change in the future. It's much harder for us to predict changes in the water cycle than temperature overall. But what's really interesting, I think, is that, we are starting to see some convergence between the climate models in terms of their projections. And we're starting to see as well some signals emerging in the water cycle. So certain places on planet Earth are getting drier. An example might be the Mediterranean region. And that's starting to come out in the observations. And that's also a place that we expect to get drier based on future climate simulations.
Well, this use of paleo data and climate models is not easy for the public to grasp. And your latest paper, though, does suggest slightly less harsh news about the worst possible outcome for our projected future if cloud modeling has made it too hot. Can we take that as good news?
Yeah, I think so. We think that the models that have, a climate sensitivity that are above 5 are probably just too sensitive. So the projections that from those particular models might be a little bit too hot. Now, it's important to keep in mind that there's still this huge range across the CMEP6 model group, that some of them, have a lower sensitivity, something closer to 3, middle of the ground. And so those might be, models to look at in more detail and have a little bit more confidence in. But yeah, I think that we may be able to rule out the most extreme scenarios in the sense that they're based on, associated with high climate sensitivity. But I will say that the biggest uncertainty moving forward is not actually model sensitivity, it's how much humans are going to emit. And that's the first order control. So even if you ask the CMEP6 models to, simulate this scenario, there's a range in that scenario, but the bigger range is between the scenarios, right? The difference between SSP 4.5, which is like the middle road one, and SSP 7 or 8.5, which are high emission scenarios, is larger than the spread between the models. So first order, the biggest source of uncertainty is what people are going to do
Find links to the papers and ideas we just discussed in my show blog at ecoshock.org. Jessica, thank you for sharing your work with us. I really appreciate it. I'm Alex Smith for Radio Ecoshock.